questions after the presentation. At that point, the committee can also ask any other questions they like. After that, we'll send everybody out. The committee will have a deliberation, and then after that, we'll see. So with that, over to you, Shani.
Thank you, Nick. And is it okay if I stand here, or where should we stand? Okay.
I guess I can sit over there.
Okay. I'm Shani Lal, and today I'm going to present my Master's in Agricultural Economics Research on irrigation as a service for smallholder farmers. And before I start with my presentation, I'll to let you all know that I'll be taking pauses in between sections, and you and the committee members are encouraged to ask questions as we go along. So let's start. I'm going to jump right into my research question of how and in what scenarios is irrigation as a service a profitable solution for smallholders. And there's a lot to unpack here. So first, let me step back and provide a little background and context of why this is important. Okay.
Hey Shani, can we record this?
Yes, there you go. First I'll be talking about why this is important. Why is this an important from an economic point of view, and what's the research gap? And here I'll be mostly talking about three main points, which are first the pain points of smallholders. There are hundreds of millions of smallholder farmers in the world, and most of them depend on rainfall for growing crops. And because of this, they face major crop losses due to climate change and drought. And irrigation is seen as one of the strategies to mitigate this problem. So what is happening is government and multilateral agencies and NGOs, they are focusing on making irrigation accessible to smallholder farmers. There are many different approaches, and one of them is farmer-led irrigation. When we talk about farmer-led irrigation, we see that a lot of focus has been on increasing individual pump ownership. And this is in slight contrast with what we observe in the real world. We see that smallholders tend to engage themselves extensively in sharing of irrigation equipment or informal water markets. We also observe that there is a growing number of entrepreneurial irrigation as a service providers who are present in these landscapes, who provide irrigation services to smallholders. So what's the research gap? So far, I haven't seen any rigorous economic study which talk about irrigation as a service, especially from entrepreneurial point of view. And this thesis is an attempt to provide a conceptual basis of this problem, which is ubiquitous and happening in the real world. Also, I am trying to explore if there is an economic rationale to this problem. So when we look at some of the relevant literature review for my study, I'm mostly dividing into two broad themes. One is around farmer-led irrigation, and here are some of the papers that give an overview of the importance of farmer-led irrigation and its different modalities in different countries and also globally. And most of them talk about how to increase individual pump ownership. A subset of this literature is increasing financing option to access irrigation, and most of that is around making solar pumps easy to purchase. And here I would like to flag one report by World Bank, and it was published a couple of years ago. It's a very comprehensive report which talks about different modalities of farmer-led irrigation, and it does mention irrigation as a service in a few sentences, and it's a 100 of pages report. The other broad theme is around informal water markets, and here we see a lot of work has been done in Southeast Asia, especially in India, which talk about how farmers engage themselves in sharing irrigation pumps. And the irrigation as a service is a kind of informal water market, but paper on irrigation as a service is very rare. And the paper I have mentioned here is Achillesa et al., and it's by our own team at Water for Food. So far, I have used this term irrigation as a service several times. So let me define what I mean by irrigation as a service. It is the sharing of irrigation equipment between farmers without farmers needing to own them. Here I would like to make 3 main points. So this irrigation equipment is mobile and can be transported from one farm to the other. The second important thing to keep in mind is the farmers or the farms that are being irrigated with this irrigation equipment are not necessarily belong to a single owner. So there are multiple owners of this farm which are being irrigated with a single piece of irrigation system. The third point is this irrigation system can be as small as a petrol pump or diesel pump, or it can be as large as a hose reel system, which is shown here in the picture. And as you can see, it's being pulled by a tractor. What do I mean by entrepreneurial irrigation as a service is, entrepreneurial irrigation as a service is a for-profit business which is run by non-farming people who provide irrigation service to smallholder farmers. This brings me to the end of the overview and motivation section. So if you have any question right now, you can let me know. Okay, great. And here I just wanted to mention that Water Food Conference is coming next week, and we'll be having a couple of irrigation as a service businesses who are visiting there, and they'll be participating in the AgTech Happy Hour. So if you would like to know more, you are encouraged to participate. So let's continue with the methodology section, and here it's the main outline of how I'm approaching the methodology for doing this study. So I developed and analyzed a decision-making model for irrigation as a service, and here I have used a crop water production function to build, and that's the basis I used to build my model. It is basically a mathematical relationship between irrigation water applied and crop yield. You can think of it like a crop response to water. And I analyze the optimal irrigation strategy and see how it varies as a function of weather, crop type, and economic parameters. So crop water production function varies as a function of weather, crop type, and soil type under the parameters. So I'll be seeing how that changes our optimal irrigation strategy. I have used a combination of both analytical and simulation method to solve for a couple of objective functions of yield maximization and profit maximization. And now I'll be talking about each of them in detail. So this figure shows a typical crop water production function, and as you can see, just looking at it, it's a sigmoid line shape, or we can say it's non-concave. So in its most general form, what we see that it's non-concave, and this shows the response of yield to the irrigation water applied. And as you can see that even when we are applying no water, there is still some yield, and that's the dry yield. Even without providing irrigation, like from rainfall, it has some yield. And in the beginning, when we apply less water, the returns is increasing. It's increasing at an increasing rate. And as we keep on applying more water, the shape of the curve changes to concave, and we get a decreasing returns. Here I have not shown what happens if we keep applying more and more water, and that you can think of it as over irrigation, and in downwards, and then the yield goes down. But I'm assuming that for my study, we are in a water constraint situation, so there will be no situation where we are going to over-irrigate. And that's for my study only. So, yeah, I think that's pretty much it. Let's move on. So, crop water production function has been approached in different disciplines in different ways. And here I'm providing 3 different ways in which crop water production function has been studied. First of them is empirical method, where we use field data or experiment data and use that to fit a functional form, and that's how we predict what is the crop response to water. The other popular method is using crop modeling, and here and this is a mathematical model, a complex mathematical model, where we use data as inputs, and we provide that to the model, and then we get the crop response to the water. For example, of some of the crop models are EcoCrop, DSAT, EPSEM, and the most, and I think it started with CropFort, so I should mention that as well. The last one is fitting functions to model, and this is mostly used by economists, where we use different functions to fit a crop water production function. And typically we see that some papers use quadratic function to model crop water production function. But one of the disadvantages of that is we are imposing that by using a quadratic function, we are imposing that the function is strictly concave, and that limits us to use like only those functions that are in the concave situation. Here I would like to highlight the one paper which is by Rad et al. They have used a cumulative distribution function to model crop water production function or represent crop water production function. And my study is based on their work. So this is what a normal cumulative distribution function looks like, and if you compare with the figure I showed for a crop water production function, it typically looks like that. So, and using a normal cumulative distribution function allows me to model both concave and non-concave part of the crop water production function. And here, the normal CDF depends on mean and standard deviation. And by changing the value of mean and standard deviation, we can shift this curve and see, and that can be used to model different type of crop resilience to weather shock and different climatic scenarios. And one more thing I would like to highlight here is by using a normal CDF, we are normalizing the yield to be 1. Like the maximum yield that we can have is 1. So that's the assumption I'm using for my study. And also the water that can be applied to one field is 1. So that's the highest amount of water we can apply to a field, and the highest amount of yield that we can get is 1. So this figure shows that when we change the value of mean, or it's represented by the symbol mu, how the CDFs change. So the first one here is the blue line, which shows a strictly concave crop water production function with a mu equals to 0. And here you can see that we don't have any non-concave part, it's decreasing returns. Then moving on to the next one, the red line, it's mu equals 0.3. We can think of it like a slightly non-concave crop water production function. And here in the beginning we have increasing returns, and then it switches and becomes like a concave crop water production function. Similar thing happens with when we keep increasing the value of mu, and it's mu of 0.7. And here the non-concave part becomes larger. As we increase the value of mu, the non-concave part gets larger. also like to address, I had a discussion with Dr. Shanabol, and she asked me this question that what happens if we change standard deviation? So when we change the standard deviation, the slope of this curve changes, and for lower values of standard deviation, the slope becomes steeper. This is a schematic diagram which shows how I'm approaching my methodology. So I have divided it into two parts: concave crop water production function and non-concave crop water production function. I think I have convinced you all that since the shape of basic crop water production function is non-concave and both of them are dealt differently in economics, so I'm going to look at both of them differently. So for concave, I'm using analytical method, and for non-concave, I'm using simulation. And for both of them, I'll be solving yield maximization, objective function, and profit maximization. So you might ask me why I'm doing this, like why I'm solving for yield maximization. It's because the focus of a lot of agronomists and government in developing countries is to increase food security. And they are more concerned for increasing yield rather than profits. And so why I'm doing profit maximization? Because in economics, especially water resource economics, we care about profit maximization, and here I assume risk neutrality. And for both yield and profit maximization, I'll be comparing my irrigation decision making. I'll be seeing how it looks like for asset utilization rate, and I'll be comparing a fixed system with a mobile irrigation system. Now let's see how I've set up my objective function for yield. So I'm maximizing total yield across all the fields that we can irrigate with one irrigation equipment, and here W1, W2 represent what I allocated to individual fields, and here I am summing all the CDFs. CDFs is the crop water production function, and it basically gives us the yield for each and every field, and it's a function of the water applied, and the shape of it depends on mu which is the mean, and standard deviation. This is subject to a couple of constraints. First is the total water, the aggregate water applied to all fields should be less than equal to W bar, which is the total water available. And the second one is, we're just saying that the water applied to individual fields should be non-zero. I think I covered most of it. Right, Nick?
So my presentation.
I just have one question. So why do you assume risk neutrality if you are considering the decision making of farmers whether irrigation or not?
So this is not for the decision maker is not farmers. So the decision maker is a larger body like a government agency who is looking at the yield maximization across the landscape. So we are not concerned about increasing individual farmers' yield. It's across the landscape how it looks like. So I guess it's a question. Moving on to the profit maximization. Here I am maximizing total profit. It looks similar to the last one, and the price for crop yield is I have considered crop yield to be a numeric good. So the price on it is 1, and I'm also considering the cost of water, and cost of water is not a function of water applied. It's a linear function. The cost is a linear function, and we have the same constraints. So here, as you see that I have inequality constraints. So I'm going to solve for Kuhn-Tucker conditions to solve for my optimality conditions. And I just want to mention, I hate Kuhn-Tucker, but still, I did this because it gave you more clarity. That brings me to the end of the methodology section. This is me, I think 7 months pregnant. seeing my results and trying to make sense of it. So, do you have any questions? Yes.
Do you think your baby will like Kuntakar?
Oh, I
She was
don't-
not pregnant with this, right?
Maybe.
What are the chances? Do you think your baby might like it? I know I'd like it.
I think she loves her dad playing guitar and she's obsessed with guitar. She'll be a musician. I don't know.
And I suppose I'd like to point out that actually the Kuhn-Tucker conditions that Shani insisted on solving, that I was not encouraging her to do it, and she actually chose to go that route. So don't blame me.
No. It's evil and yet useful.
Well, I think I don't know, I mean, this is maybe, given the frequency of corner solutions, you
Exactly.
really need.
Yes,
Precisely.
exactly.
No.
Exactly.
Evil yet useful.
There you go.
Okay, so committee members, should I proceed? Great. So this is how I'm going to present my results. It gets a little complicated, that's why I'm clarifying it in the beginning. So first I'm going to look at the concave profit reduction function, where I have used analytical method to solve for my yield maximization and profit maximization, and then I will be comparing it to a single field case. And in the second part, I'll be looking at the non-concave profit reduction function, where I use simulation to solve for both yield max, profit max, and compare it to a single field case. So now this is the result, like this is the first order condition that hold and satisfy the Kuhn-Tucker conditions for my yield maximization, and there is just one valid solution. So what I did, that I first set up the Lagrangian and then I took a derivative. So this is what I got, and what this means is phi represents the derivative of profit reduction function, which was a normal CDF. So this is a normal PDF, and the optimal water allocation is W bar over I. And here I would like to mention that I have assumed all fields to be identical. That's why we get this W bar by I, which is equal to the shadow value, and the shadow value is always positive. So what do we mean by shadow value? So when we loosen the constraint by 1, that's the change we see in our optimality condition. So we see that it's always going to be positive. So my result says that whatever water is available to us, we are going to use all of them. And the optimal water allocation is to equalize the marginal physical product, which is this phi. And since I'm assuming all fields to be identical, it's going to be equal for all the fields that we have under yield maximization for concave profit reduction function. So before moving to the profit maximization, I just want to show what the simulation results look like for a concave. So it's exactly the same what we predicted from our analytical method. So when we see the water allocation figure, as we increase the water availability, the water allocation will increase to all the fields, and here you can't actually make out which is field 1, field 2, field 3, because all of them coincide. Similar thing happens with the marginal product. It's same for all, like we equalize the marginal physical product, and this is a portion of the normal PDF that we are seeing here. Moving on to the profit maximization for concave, here I find 3 different cases which hold and satisfy the Kuhn-Tucker conditions. First is the corner solution, where the cost is low enough. So what this looks exactly similar to the yield maximization case. So here the optimal water allocation is to use all the water that we have. And you can see the value of marginal product, we are using all the water, like W bar by I is greater than the marginal cost. Case 2 is the interior solution, where both the constraints bind, and here we will irrigate until we reach reach the point of where value of marginal product equals marginal cost. And since it's a concave crop water production function, this is the global max. And here we are not going to use all the water, but we will be irrigating all the fields that are there in the landscape. For case 3, it's the other end of the corner solution where the cost of water is very high, and in this, like even at 0 water allocation, the cost of water is very high. So we choose not to irrigate at all. And here, no fields will be irrigated and we will not be using any water. Now, when we compare it to the case of single field where I equals 1, we find that the asset utilization rate is the same for both single and multiple fields. Why is that? Because we are going to use all the water. It's in yield maximization, whether it's single field or whether it's multiple field. The total yield is higher in case of multiple fields, and in a moment I'll show you why. So this is a strictly concave crop water production function, and what this means is the function of the average is greater than the average of the function. And this means that if we have a concave, strictly concave crop water production function, then and this what I have seen showed is for a 2-field case. And if we have a 2-field, the yield that we get from distributing that water in 2 different fields is always going to be higher if we use that water, all the water on the So concave crop water. So now coming on to the profit maximization, we have two solutions: the corner solution and interior solution. And in both of them, total profit is going to be higher in case of multiple fields. And the asset utilization rate is same for corner solution, but it's going to be higher in case of multiple fields. Here I'll just give you a few moments to look at the summary of what all I talked about regarding my concave results. Okay, let's proceed. Again, I would like to remind you all, what do I mean by non-concave crop water production function? As we increase the value of mu or mean, we are increasing non-concavity, and you can interpret it like we are going from a rain-fed or supplemental irrigation to a more drier conditions, where we need a lot of water to get any yield response. So these are my results for non-concave crop water production function where mu equals 0.3. And first let us look at the left hand side, water allocation. Here red dots represent field 1, green hollow circle field 2, and the blue cross is field 3. So as we increase the water availability, the water allocation to field 1 increases, then it drops down, and there we add the second field, and we are irrigating both of them equally, like we are allocating same water to both field 1 and field 2, and it reaches a point where it drops, and now we have added a third field, and here we are irrigating all 3 fields equally. And this is increasing, but it's non-monotony. And where we see this drop, why is it happening? So for that, let's look at the marginal product graph. So here, as we increase the water availability, the marginal product is increasing, and then it reaches its peak, and then it starts decreasing, but still we have not added the second field. And why is that? Because we are waiting for the water to be enough so that we can offset the non-concave part field 2. So we will not be irrigating until we have enough water to get to the maximum marginal product point for field 2. And that's the point where we start irrigating both fields equally. And similarly, that goes for third field. So here, two things to keep in mind is, this is yield maximization, so we are using all the available water, but we are not giving the same amount of water to all the fields. Like, it highly depends on the water availability. Now let's look at the non-concave crop water production function for mu equals 0.7. This is a highly non-concave crop water production function, and here you see a very funny diagram. So let me explain what is happening. So when we increase the water availability, the water allocation to field 1 is increasing. Okay, then it reaches a maximum point. I mentioned in the beginning that the maximum water one field can get is 1. So at that point it becomes like flat. It's not going up, and we have not yet started irrigating field 2. But we reach a point where we are giving all the water that we can give to field 1, and then we start irrigating field 2. Once we have water more than 1, that's when we start irrigating field 2, and both field 1 and field 2 are getting different amounts of water. Then you see there is a jump for field 2, like this green hollow circle, and then now you see a jump, and here you see both red and green hollow circles. So at this point we have started allocating same water to field 1 and field 2. Similar thing happens, like now we max out for both field 1 and field 2, and after that we, like once we have water availability of more than 2, then we start irrigating the third field, but still we are not giving the same amount of water to all 3 fields. And why is it happening? It's because of the marginal product. So if we look at the right hand side graph, we see that in the beginning for field 1, the marginal product is increasing. So we are allocating all the water to field 1 until we get to a point where the marginal physical product becomes like it's becoming flat. So that's where we start irrigating the second field, and then once we cover the non-concave part of the second field, that's where we add the third field. So
Non-concavity is messy.
yes, and that's why many people assume strictly concave crop production.
That's right. But it's hard, it's how do we induce it? It's difficult.
Yeah, I'm afraid, did I make myself clear? Okay.
You did. It's good.
So this is a surface 3D surface plot, and this is basically showing my yield, the objective function for yield for optimum water allocation. And here, like there's a slope to this surface plot, and we see that as we increase the value of mu or mean, and as we decrease the water availability, the yield will drop. The yield is decreasing, and this portion you can interpret as like a concave crop water production function. Now similarly for profit, as we keep increasing the value of mean and we decrease the value of water availability, we see that the profits are decreasing. And the breaks that you see in the surface plot is the point where we are indifferent, where we are irrigating 1 field or 2 field, and the second one is for 2 field or 3 field. what all I explained in the graph in the form of my results. So for yield maximization, non-concave crop water production function, all the water that is available will be used because marginal physical product is always positive. But all the fields may not be irrigated. It highly depends on the value of mean and the water availability, and the fields that are irrigated may or may not receive the same amount of water, like we saw in the case of mean equals to 0.7. For an individual field, an additional unit of available water may increase or decrease the total water applied. So what this means is, like for field 1, first we were increasing the water, then we decreased it. And so that's what it means, that even if we are increasing the total water available, it doesn't mean that we are always going to increase water in that particular field. And the optimal choice will be to apply this additional unit of water to the field with the largest marginal physical product of water. The choice to use marginal water on previously irrigated field or to add a new field depends on comparing the marginal physical product of water for n fields and the scenario for n+1 fields. Now coming on to the profit maximization non-concave results, it's similar, like the choice to use the marginal water on previously irrigated field or to add a new field depends on comparing marginal value product of water, because it's profit maximization, and for n fields and the scenario for n+1 fields. And even here, if we increase the total water available, it doesn't mean that the water allocated to any field is like it's going to increase. It might remain same, it might go up, or it might go down. And total profits will stay the same or they will go up. And the asset utilization rate, it also might remain the same or go up. Now when we compare it to a single field case, the yield maximization, so the total yield may remain same or increase because it depends on the shape of crop water production function. So yeah, it might remain the same as a single field, or it might increase in case of multiple fields. And the asset utilization rate is the same because we are going to use all the water, and you can think of asset utilization rate as the pump, how the pump is being operated. So if it is being operated to its full capacity or not. So now comparing the profit maximization case, here also, like in both corner and interior solution, the total profits may remain same or increase in case of multiple fields, and the asset utilization rate will remain same for corner solution, but it will it may remain same or increase in case of interior solution. Now I'll just give you a moment to go through the summary of everything we talked about in the results section. Should we proceed?
Maybe.
This brings me to the end of the results section. I know that was a lot and really complex. So if you have any burning questions, or if I didn't explain something, So now I'm going to talk about the policy implications of the study. And first, before I start, I would like to acknowledge and thank Sonia. She provided some great feedback on the policy implication section. And I hope I have toned down the way I wrote it in my thesis. So the first one is around the cost effectiveness of donor funds. So in the background, I talked that there has been a lot of efforts by government, donors and multilateral agencies of how to increase irrigation access. And what I feel that their intent is not to increase pump ownership, but that's the thing that they view as a way to increase small scale irrigation. But my results show that if we allow that irrigation equipment to be shared between farmers, then that can be potentially a good way to use the donor funds. That can be a cost-effective way to use the donor funds. And I also and what do I mean by cost effectiveness is if we have irrigation equipment, what's the return on that if we are using it on a single field and when we are moving it around in multiple fields. The next one is supporting entrepreneurs who provide irrigation as a service. So right now, like my results show that if we share the irrigation equipment, it might be more cost effective. But this sharing is a kind of informal market and there's an issue with scalability. So irrigation as a service providers or entrepreneurs who are doing this as a business, that can potentially be a good way to do this irrigation as a service, and it can be a better way to support irrigation as a service and see what's the return on their invested funds. So far, I have talked about smallholder irrigation and how to how irrigation as a service can be done in smallholder setting. But the model that I developed is general, and I haven't, I didn't assume about the field size or the pump capacity. So this can be translated to larger farms or medium farms, like which are tens of hectares of farm, and if the pump capacity is high, like in a hose reel system, we can pretty much use these results in large or medium farms as well. Now, talking about limitation, in my study, I have used a lot of assumptions, and as an economist, I think my job is to make assumptions. So, but one assumption that I would like to...
Yeah, love it. Wait till you meet a theoretical mathematician. They will teach you how to make assumptions.
One of the assumptions that I would like to highlight is I have not considered the time of moving the equipment from one field to the other. And I think that's a very important, that's a very strong assumption because that would impact my results. So right now you can see that if I have 1,000 fields, I'm saying that you should share the equipment to 1,000 fields, but that is not practical. So once we add this time constraint, then we'll get some realistic results, and I think that's also a good extension of this work to add the time constraint to this model. Some other work would be to use some empirical data and do some empirical analysis of this work or some piloting. And also using, I've used a normal CDF to see if there and to use the data and see if this fits and if we can use a normal CDF in the real world scenario. So now coming on to the summary of my whole presentation. So I developed an economic model for irrigation as a service. Here I talked about the importance of crop water production function, the curvature of crop water production function, and how different type of climate will change our decision making, irrigation decision making, in case of single field and multiple fields. And I show that irrigation as a service may be relevant to a broad range of situations, And especially if we see a concave crop water production function, which can be viewed as a geographical area which is rain-fed, or where supplemental irrigation could be very beneficial. Having irrigation as service in those parts of in those parts could be a very yield maximizing and profit maximizing as compared to having a single pump. And my result also had some important policy implications of cost effectiveness on donor funds and the return on the invested funds. And also, I also talked about the scalability, that the model that I developed can also be used for medium or large farms. Now I would like to thank my advisor, Dr. Nick Brozovic, for helping me with my research, my committee members, Dr. Karina Shangol, Dr. Sonia Balasubramania, and Dr. Taroliano. Policy team members, Kamsha, Ankit, David, Grace, Harshni, Lacey, Natasha, Rachel, Raisa, and Renata for always supporting me and being my cheerleaders. The Department of Agricultural Economics, who gave me this opportunity to combine 2 master's degree, and the Dirty Water for Food for giving me the funding support. Lastly, I would like to thank my family and all my friends, and also the audience who joined on Zoom for coming to support me. Thank you.